Down, please. We would like to start. Okay, so welcome to the last session of this very nice conference. My name is Ralf Gebauer. I will chair this last session. And we start now with probably the speaker who has had the furthest trip to come here to San Sebastian. It's Alexandre Rocha from Sao Paulo, so a long trip. Yeah. And he will talk about simulations of biosensors at the atomic level.
So thank you very much. I would like first to thank the organizers for inviting me. What I'll be talking about is a little bit of the work that we've been carrying out in Brazil. So before actually I start, I'll reverse the order and I'll do a little bit of advertisement. So I come from Brazil. It should be a relatively long trip, but it was much longer because I was actually in the US, so I came back to Brazil and here, so I was traveling for more than 40 hours to get here. We are based in an Institute of Theoretical Physics, which is part of one of the universities in the state of São Paulo, which is one of the richest states in Brazil, which means we still have a little bit of money to do research. But the good thing is also because we are very far away from the Amazon, so there's very little risk that Leonardo DiCaprio might put some fire on us. All this to say that we have a branch of ICTP. So ICTP has a few branches outside of its main campus in Trieste. Ours is called South American Institute for Fundamental Research, and as ICTP, we organize schools. Most of them are really guided towards high energy physics, but next year, or actually this year, we're going to have a school on density functional theory, electronic structure. This is the typical school that is hosted by the people in the Fritz Haber Institute, the FHI Ames group. One year is hosted here in Europe, another year is hosted somewhere else, and we are hosting it this year. So if you're a postdoc or a PhD student and want to come to Brazil for a couple of weeks, we fund people to come. So we have money to bring people as well to attend this school. So it's going to be a very nice 2-week school in July, which is actually winter in Brazil, but it's never too cold. So this is my advertisement. So watch out for the call for applications for this school. And will be open soon for the upcoming event. Okay, so this is my advertisement. So let's talk a little bit about science and the work we do. So the story I'm going to tell you today started a long time ago, not in Brazil, but I have some connection with it because Erwin Schrödinger in the late 1930s was living in Ireland, and in fact he gave a series of lectures in my alma mater, which is Trinity College Dublin. About something that is not so much related to physics, but he coined a term that came out in a book called The Meaning of Life, which is the idea of a genetic code, which is the idea that the information to construct any living being is encoded in some form of molecule that he called a aperiodic structure, because it has some repetition, but this repetition has to somehow contain some information. So it cannot be like a very crystal, right? So it's an exact crystal, but it has some structure to have some information encoded in it. And we know this molecule now to be DNA. So DNA in principle it's like a cooking book for constructing any living being. So the idea is that, well, maybe if we are able to get this information, decode this molecule, then we are in a position to understand any life form, right? So that's the kind of holy grail of biology. And actually this effort, although the structure of DNA is known since the 1950s, to actually understand the whole sequence of a human being, which is composed by 3 billion of these molecules here. So the 4 molecules that are forming this DNA, and they form in a double helix structure, which is probably the most known molecule in biology, are 4. So you have a molecule which is thymine, another one which is adenine, cytosine, and guanine. And the idea is actually to try to find out what is the sequencing of a particular human being. Now, this opens up the idea that you can actually go into your doctor, ask for your DNA to be sequenced, and then get this information back and know, for example, any predisposition to a genetic disease, or to have some form of medical treatment that is specially guided towards you. And this is already there is some sort of things going on already, for example, in cancer treatments, where by getting this information, you can actually tailor the treatment towards a specific patient. Right, so this is really something that is sort of the idea that you can have personalized medicine towards each patient. Now, in order to do this, then you have to be able to do it fast and to do it cheaply. Now, the first sequencing was done in the the early 2000s, so the beginning of this century. It cost just $100 million to do the first one. But now the cost has dropped dramatically to something very close to $1,000. Now, it's still too high using the current methods to be able to become mainstream, right? So the idea is that we need to find a new method to do sequencing, which will bring this cost down, and then it can really go into mainstream medicine. So the current method is known as Sange method. It's it's an optical chemical method, it's very cumbersome, it's very cost intensive, and the idea is maybe we can find a new way to do this more cheaply. So what is this new way? Can we find this way? And now I'm going to make an analogy for this new method, which is going to give my age away, because if you know this, right, or if you use one of these, then you are either as old as I am or older. So this is a cassette tape. People used in the old times to listen to music. You needed a cassette tape, one of these to play the cassette, and typically a pen as well to get your cassette back to the original starting position. But the idea is that you take this tape, which is akin to an analogy to DNA. You pass this tape through a reading head, and somehow, as the tape is passing through the reading head, you get this information out, right? This might sound crazy, but it's actually available commercially. The idea is that you pass DNA through a sort of a membrane, use the same idea that biology uses, which is to get DNA out of the nuclei. You need something like this. You have a hole in your membrane. DNA passes through the membrane, and in this case, what you do is, as the DNA is passing, the DNA is charged. You are carrying ions as well, so you have some ionic current, and so you can get the information, or you can try to extract the information about what is the molecules that are inside, or the bases that are inside, based on the ionic current that is passing through. So this is the whole idea of a company called Oxford Nanopores. This methodology is already available. There are other possibilities, which is, instead of using a biological membrane and a biological nanopore, or biological hole, you can use solid-state materials, such as, for example, in Charles Lieber's group, they proposed something similar using silicon nanowires. But our idea is a little bit different, right? So instead of using ionic currents, maybe what you can have is an all-electronic device, right? So the idea is, instead of trying to measure ionic currents, what you do is your device or your membrane is also acting as an active region, in the sense that you can measure currents, electronic currents flowing through your membrane, and the electronic current is going to give you a signature of the molecule that is passing in there. Right? So if you have some molecules are different, the energy levels of these molecules are different, and so you can have some information about that particular signature. This was a proposal that was put forth maybe 15 years ago by Max de Ventre. It has evolved since then. One of the problems is that if your membrane is thick, then you have current that is flowing through more than one base at a time, so you have to think about some way to get rid of these spurious signals of the other bases. But one possibility is to actually use the thinnest possible membrane you can think of, which is graphene. So the graphene has this great property that is highly conducting, is super strong. So if you can use graphene, and it's super thin, so if you can use graphene as your membrane, then it has, in principle, all the properties that you require. So if you make a hole in the system, and then you pass the DNA through it, maybe you're in a good position. Actually, this was first proposed by Henk Postma in 2010. Not through a nanopore, so not making a hole through the nanopore, but by making a trench in graphene. This might seem at the time it's easier to think of, but it's much harder to do experimentally than do a nanopore. So experimentally, there have been some developments. So people actually Maria Drindrich and Sis Decker's group, they have actually managed to make nanopores and to detect DNA passing through. So you're actually able to do an electronic device where you know whether a DNA molecule is actually inside the pore or not. But you're still unable to differentiate between different bases, right? So you're not able yet to determine that the molecule that is inside is either A, C, T, or G. Okay, so where do we come in, right? So we're theoreticians. We want to simulate a device like this. So from a theoretical point of view, this is like a simulator's nightmare, right? Because it's a dynamical system. It contains a solid-state material. It contains water. We want to do an electronic device, so we cannot really calculate this classically. We need the electrons to be present, or at least in part of the system. So it's really, and it's extremely large, right? So how do we go about simulating something like this? Well, the idea is the following. So first of all, this is what I'm going to call a realistic device. So from an experimental point of view, this is not very realistic, but for us is probably as realistic as it can be done. So we have graphene, we have a pore, we have a DNA strand passing through. We want to flow current through this device. We have water. The counter ions are not visible, but they're present as well because we want to be in an aqueous solution that is akin to what the DNA is present. And the DNA is charged, so it actually has to have some ions to balance the charge. So all this has to be contained into our model. So first of all, we need a theory to calculate the transport. Nick did a very good job of giving an overview of what NEGF is. So we use NEGF as well. So the idea is that you have electrons that come in from some electrodes. They pass through the scattering region, which is going to be this box that I just showed. And then electrons flow out on the other side. We need a Hamiltonian to describe this. In principle, we have to apply a bias for the electrons to be driven. Our calculations that I'm going to show here are for very low bias. So the limit of zero bias, but it can be done for higher bias. And we need, in principle, a Hamiltonian to describe this problem, right? So we toss this into our toolbox of NEGF. We can calculate then the quantity that we really want to calculate. This is the Green's function for the scattering region with these self-energies. So as Nick was pointing out, the self-energies are somewhat fixed. They're not altered by the effect of the scattering region. So they only need to be calculated once. But everything is calculated self-consistently. And once we have a self-consistent Green's function, which is dependent on the charge, so the Hamiltonian is dependent on the charge, we can calculate the transmission coefficient, which is nothing more than the conductance. So once we obtain the conductance, this is essentially the quantity that we want to use as our signature of the presence of a molecule there. Okay, so now which Hamiltonian to use? We can use a model Hamiltonian, but the whole idea is to do something that is as realistic as possible. So the point is to take the Kohn-Sham Hamiltonian as a single particle Hamiltonian and use that Hamiltonian to calculate the transport. The whole point here is that the introduction of an external potential, typically we introduce the external potential as the potential coming from the ions, but we can use it also to include, for example, if you're using a non-equilibrium potential, then here also comes in the potential coming from the external bias that is applied, but we can also add extra potentials to this problem, right? So if we have an external classical potential that could be added to this, it would come in here. So the whole toolbox works in a kind of self-consistent way. So the whole idea is very similar to typical density functional theory, but instead of calculating the charge density using a diagonalization of the Hamiltonian, as typically it's done, because our system is open, then we use the Green's function to calculate the charge density. But the rest is the same. So once everything is converged for a certain bias, we can get all the properties, all the physical properties of this system. We package this into not Trans-Siesta, but SMIGO, which is another transport code that we have developed. But the whole idea is very similar. So the whole process is the same, although we have a different implementation. But the point is, okay, but the system is still too large, right? So we want to simulate something very, very big with water. And then we can go, since we're trying to simulate biological systems, maybe we can understand, get some information from guys working in biology. And they have developed this very neat idea where you say, oh, look, there are some regions where electrons are important. There are regions which electrons are not necessarily that important, but they must come in, they must be accounted for, right? So in biochemistry, if you're looking to simulate, for example, reactions using biomolecules, which are huge, typically what you need to do then is say, okay, the active region is typically a region with a few atoms, and the rest is only coming in as a potential to screen everything, right? So we can do the same, right? We can separate our system and treat them in two different footings, one classical and one quantum mechanical. This is known as a method known as QMMM. So we split our system into a classical region and a quantum mechanical region. I'll go into that in a bit. But the whole idea is then to use the best of both worlds, right? So to use quantum mechanical methods to get everything properly described, and in our case, we really need the electrons. But at the same time, we use a piece of the system in classical methods because we can do very, very large systems. So what we want to do is to do something that splits both of them. Splitting the system is, in a sense, is a bit of an art, right? So you have to test what is really necessary for the quantum mechanical part and the classical part. But the idea is the same. So we take our Hamiltonian, we have a Hamiltonian which is quantum mechanical, a part which is classical, and an interacting part here. And when we have to be careful, especially when we have bonds, because if we want to consider a piece of the system which is bonded as classical and a piece of the system which is bonded as quantum mechanical, then you have to break a bond. We use a methodology that basically, when you break a bond, you substitute these bonds by a fake hydrogen atom. But in principle, you have to be careful about this property. And then everything comes in as a classical potential for the classical part, right? So in our Kohn-Sham Hamiltonian, essentially what we're doing is we're taking our Kohn-Sham Hamiltonian for the transport problem, and then we add an external classical potential to our system, right? And then the whole non-equilibrium Green's function toolbox works exactly in the same way. So everything is calculated self-consistently with this frozen charge distribution coming from this external potential. So what is this QMM method actually is packaged inside Siesta. It's a collaboration with Pablo Ordejon, who might still be here. It basically is packaged into Siesta, and then we put it into our transport code as well. So how do we select the system? So in our case here, for this very simple system, what we do is we choose all of the water to be classical. We cut the DNA, which is not inside the nanopore, and also considered to be classical. All of the counter ions except one counter ion, which is going to balance the charge of the DNA inside the pore, is classical as well. And then the rest is quantum mechanical. So all of the graphene plus a basis that is inside is also quantum mechanical. So okay, with this, then what is the idea, right? So we want to simulate the system. So this is the typical structure that we have. We have graphene with a nanopore, in this case saturated with hydrogen, which is the simplest possible saturation we can have. We put the DNA inside. It's actually, there's water around and there's a molecule attached. And the first thing we do is we do a classical simulation of this problem. So we allow everything to move. We keep here the graphene frozen. I'm not going to show you, but even if you allow the graphene to move, there's very little change coming from the graphene to the transport properties. So we just keep it frozen for practical reasons. How much time do I have? Okay. And then we do a simulation. So we do a classical simulation, very long classical simulation, allowing these molecules to play inside the nanopore. And then from this classical simulation, we extract a very large number of snapshots. So we have, at uncorrelated snapshots, we extract a snap of uncorrelated position structures. We extract this snapshot, and we use this structure to do a QMMM calculation. Right? So we do a quantum mechanical calculation where we select the quantum mechanical region, the classical region, and then obtain the transport properties. Right? So just to have an idea, so this is typical structures that we obtain. So you can see that the structures are very different, right? Even, I mean, they play inside the rotate a lot. And this is especially because what we do is we use a single strand of DNA, and a single strand of DNA is highly unstable, so it's very, very flexible. At the same time, if we only use the double strand, which is much more rigid, the fact is that we will only be seeing the backbone of the system. The backbone is all the same for all the bases. So it would be much harder to differentiate between the two molecules. So there's a trade game between the choice of something that it has a lot more configuration space and something that has more molecular levels available for us to probe. So from this, we extract about 200 of these, 200 of these, 200 of these, 200 of these, and then we will do distribution of changes in conductance. Right, so we calculate for each one, we do a single shot transport calculation, including the QMMM effects. So this is a typical snapshot of a full structure where this is the structure that we use as our calculation for the electron transport. So you can see that we saturate with a fake hydrogen, and everything else is calculated classically. So what do we get? Right? So this is a distribution of conductances, changes in conductance for a molecule that is somehow inside. So they can fluctuate inside, a little bit out, a little bit into the nanopore. You can see that there is a small difference in the peaks, but all of them are more or less the same, right? So the variance or the distributions are become pretty much indistinguishable. So this is bad, right? So this is a kind of a negative result in a sense. But still, we would like to understand where is this kind of so the families are being joined together, right? So adenine and guanine, which are these two structures, which they come from the same family, right? So you can see that they have two rings. They fall more or less around the same region. And then thymine and cytosine, which only have one single ring here, they fall in changes in conductance around the same region. And then what we do is we look at what is happening in terms of changes in charge on the molecules. So we see that there is a small charge fluctuation, which is following so it's correlated with the conductance, right? In a similar fashion of what Nick showed for the forces, right? So charge accumulation on the molecule is actually driving the changes in conductance in the same fashion that it's correlated with the type of molecule that we have. And what is happening actually, if we look at the charge distribution on the pore, is that we see that what we're seeing is that there is some charge transfer between the pore and the molecule, and this change in local chemical potential is really what's driving the difference in conductance. So the problem here is that the graphene is highly conductive, right? So what we're seeing is that we're only seeing small changes in conductance on a highly conducting sheet. So the idea is that maybe we can drive much larger changes in conductance by having something that it's not really highly conductive in a sense. So one possibility, before I show you a little bit more results, so what is the effect of the water? So when we put the water in, the water has a crucial effect to, even if the classical water, to change the positions of the levels. So actually what happens is that if we don't put water into our system to do the simulations, then typically what we see is that the energy levels of the molecules are very, very close to the Fermi level. And then when we put the water in, then the energy levels actually go down in energy, and they become much, much closer to something that is saturated, which is really the correct effect. So water here, even a classical water, is really important to stabilize the structure, at least to stabilize the charges. So we would see a much stronger effect, but it's a fake effect if we included the water in. So one possibility is actually to reduce the dimensionality, so go to a one-dimensional system, and we can do this by including topological defects in graphene. So the idea is that you can create a nanowire, an effective nanowire with a nanopore, and then resonances will show up, and then sensitivity actually goes up, and the distribution of the sensitivity are here for each one of them, so we can distinguish in principle between the different nanopores, the different molecules inside the nanopores. And we also can see that the conductance or the sensitivity is highly associated with the binding energy of the molecule inside with the nanopore. So the stronger the binding, the stronger the sensitivity. But instead of using a nanopore and making something that is highly difficult to make, maybe we can move on to something a little bit different. And the idea is that we go back to this idea of a trench, so a nano gap, and we can saturate the edges of the nano gap with different functional forms. For example, we saturated with nitrogen for this guy, and we can put then the molecule inside, again with water, do the simulation. We find that without the water, we see a very large difference between nitrogen and hydrogen. So nitrogen actually improves quite significantly the conductance. But I think what was really interesting here is that when we put the water in the system, then, for example, in the other case where we have a highly conducting system, the water only has the effect of changing the positions of the energy levels. But it has very little effect on the transport itself. So if we do a layer of quantum mechanical water around the molecule, there is very little change on the transport. So what we find is that even if we put a quantum mechanical layer of water around the molecule, essentially either electrons are flowing around the graphene nanopore or through the molecule itself, but no transport is flowing through the water. Now, in this case here, where we have a nanogap, then basically it's a tunneling device. So either the electrons will flow between, through the molecule, through the water, or not flow at all, because this distance is much larger than you would have any type of transmission. In our case, we guarantee this because this is much larger than the basis set that we use for our calculations. So it's basically 0 if you have nothing in between. And then we do a calculation where we introduce the system with and without water. So what we look here is what is the role played by water, like the real role played by water in the conductance itself, right? So if you look at this graph, this is the total transmission of the system averaged over many configurations. And then this is the setup where we only put classical water in. So this is a system where we put one layer of quantum mechanical water, and this is a system where we put only one layer of classical water. And we can see that, well, the curves are very similar in shape, but the orders of magnitude are very different. So the water is, in a sense, probably playing a very drastic role here. And so how we see this is we plot the local currents and the contribution to each one of our elements into the local current. So we have a situation where we calculate the local current of the full system with different bases. So each one of the colors here is with different bases. Then we calculate only the contribution coming from electrons that go from the electrodes into the molecule and out. And we get something like this. But the interesting thing is, if we calculate now the contribution of all the electrons that are going here, the molecule is in here, but what we're saying is that we only calculate the contributions between the electrons that are going here through the water and out, and we see that they are of the same order of magnitude as the water of the molecule itself. Right? So here, in a tunneling device, the water is contributing as much as the molecule itself, which in principle is a bad thing, because water is always going to be present, but at the same time is interesting because what we're saying is that even though there are no levels coming from the water, explicitly, the tail of the wave function of the water is contributing to the electronic transport. And we can look at the currents flowing in a slightly different fashion. So here we're really looking at the local currents. We can see that most of the current seems to be flowing here, but it's because the current flowing through the water is actually very well distributed around the molecule. So it's flowing around the molecule and into the other side. There's also a strong contribution of electrons that actually go from the water into the molecule and out again. So this is also contributing to the effect. And so what is happening is these two things come together to give you the full electronic picture, or the full electronic transport picture for this problem. So still we get, again, a good sensitivity and a good selectivity. So depending on the energy, we get a selectivity of even about 250%. So things become better. There have been some experimental efforts to actually to obtain something like this, so to obtain a trench instead of a nanopore, which I believe is something that is much more, or at least now I believe that it's going to be much more efficient. And with this, I'll conclude by saying that we have this methodology that combines electron transport, density functional theory, and QMMM to calculate, these very large systems typically in a solution. We can then include these environmental effects. We can calculate things which are charged with some counter ions. They have a very strong effect in the transport properties. They stabilize everything. They stabilize the transport in a system where a classical or strongly conducting system. But especially when we have a tunneling transport, water actually plays a very active role in the electronic transport, so not just as an external potential. These are the guys who have been contributing with this work that has been going on for quite some time. And with this, I'll thank the people who paid the bill at the end of the day. And thank you.
Thank you very much. Other questions?
Thanks for a very nice talk. Could you comment on what you think would happen if you break the electron-hole symmetry in the electrodes for the graphene case? Or I mean, gate the thing.
If you gate it. Yeah, so in our case, our gate, so here what we call, here we don't gate it we don't really put an external potential explicitly. We only look at the change in Fermi distribution. Now, our graphene, it is already electron-hole symmetry broken, right? Because we're doing it with DFT, so the symmetry is not perfect to begin with. But we can clearly see that so our electrodes is our graphene, which is something that it's not ideal, but we would need to put gold electrodes. But the key point here is that most of the effect is coming really from the scattering region. So there's no, since we're looking only at zero bias, then there's not really a big issue there. But I agree that if you break the symmetry, we really need to have more realistic electrodes to do that. Then we would really have a source that does not have this problem that you're creating sort of a mini gap coming from the electrode of graphene.
Okay, I thought you had a question.
A very quick question. Your graphene is fixed,
yeah.
And I guess you fixed it so it doesn't do like this.
Yeah.
And how much would your plots change if you would allow graphene to go up and down?
So I don't have the graphs here, but what we do is we do graphene we allow graphene to move as well. And the thing is that because of the fact that this is a very short range potential, right? The fact that when you move graphene up and down is a long range scatterer in a sense. It's a short range scatterer. So if it's a short range scatter, it does not couple K and K prime. So there's very little scattering in this region. So around the Fermi level, there's very small change if you allow graphene to move up and down. So we have some calculations on that, on just pure graphene moving in a solution, and there's very small change coming from that. So that's why we keep it fixed.
Other questions?
So you have a study that shows there's a hole in graphene and DNA going through. In experiment, how do you suggest this hole to be created? And according to the method, what would the termination of graphene be, and how do you determine the termination? Because graphene can react with everything and anything that is in the environment, and you can have a mixture of oxygen, nitrogen, hydrogen terminating the edges of graphene.
Yeah, so we use so here in these experiments, what they do is they just put the graphene inside a TEM and then shoot a TEM, the beam of the electron of the TEM. They just use that to make the hole. So it's about at the moment they get something that is about 5 nanometers. Actually, they managed to make it smaller than that. But this is the typical way to make it. So you use an electron beam to make the hole. So these are experimental results of the nanopore.
And when they use the electron beam, how do you know what the termination of the graphene is?
Yeah, they don't know. That's a very good question. So they don't know how the termination. So that's why I called it realistic, is because obviously, if you use an electron beam, there's no way to control the fact that our nanopore is super symmetric. There's no way to control this. And what experimentalists believe is that because you're in a solution, the most likely termination that you have is OH groups. So we have some work where we put OH groups. Actually, OH groups are better because they actually make the binding with the DNA molecule stronger. So the molecule tends to bind via some hydrogen bonding between the pi orbitals of graphene of the DNA with the termination. And so in principle, that actually improves the sort of sensitivity of the device. But again, I mean, the experimentalists don't really know whether it's there, but that's what they believe, that it would very likely be OH groups.
Okay, so
Thank you.
thank you very much, Alex.
Yeah.
So let's thank again.